Hi, in this video we're going to talk about some differentiation rules. And so the basic idea here mentions in this first paragraph that when we use that definition of the derivative and we find a derivative of a function, you've probably noticed as you did some of the problems that you get similar things that happen over and over again. And so the idea here is that you would notice what those things are that happen and make some generalizations and then just memorize those results. And so that's what we're going to kind of start with here. So our first example here is just a constant function. So this one's pretty easy to use the derivative definition to find the derivative. So we'll go ahead and write this out here. So you should have this definition memorized. Limit as h approaches 0 of f of x plus h minus f of x all over h. That's just the definition for every derivative, provided that limit exists. And then if we go ahead and apply that to this function, the f of x plus h, well, no matter what we put into the function, the output is c, so that's c. And f of x is also c, so we have c minus c all over h. And then if we simplify that numerator, that's just 0 over h. And so what we have here is a fraction where the numerator is equal to 0 and the denominator is not equal to 0. The denominator is approaching 0 but is not equal to 0. So that function right there, 0 over h, that function just simplifies to be the 0 function. And as h approaches 0, 0 is 0. And so really what I've done right there is just prove that for any constant function, the derivative is 0. That should make sense if you just think about what a derivative is, remembering that a derivative is a slope. And so if you think about a constant function and just visualize that and think about the derivative, you should realize that the slope is 0. But the idea here is that once we know that, we don't have to keep doing that limit definition anymore. So the next part here for the notes is some basic function derivative shortcut rules. So I'm going to go ahead and fill in that first one there. So that notation, we've talked about that before. This d dx notation here means the derivative with respect to x of whatever function is inside that parentheses, whatever it's being applied to. So the derivative with respect to x of the constant function c, and that is equal to 0. All right, so once we know that, we don't have to keep doing that over and over again. So you can see here a few other rules that we're going to try to generalize today. So let's go ahead and look at some more examples. All right, so example 2 is the second one in that chart where we just have f of x equals constant times x, where k is a constant. And again, just thinking about this in terms of the derivative being slope, you should be able to think about that that is the equation of a line, y equals mx plus b, where the m, the slope, is k. So it's just a line with y-intercept 0 and the slope is k. And remembering that a derivative is slope, we should expect that our answer is just going to be k here. But let's go ahead and use that limit definition to actually go through the process and prove that that really is what we get. All right, so f of x plus h minus f of x all over h, and we have that limit as h approaches 0 out front. When I put x plus h into the function in place of x, I'll have k times x plus h minus, and then the original function, f of x, kx all over h. And just to save some space here, there's some algebra that you should be able to see is going to happen here. So we're going to distribute that k through. So we'll have kx plus kh, and then we've got a kx term at the front and another kx term at the back that are going to end up canceling. So just to save some space, I'm going to skip that step in the middle there of distributing through and then canceling. So then I'll be left with kh over h. The h's cancel, functions agree at all but one point, and we've just got k, and so the limit as h approaches 0 of k, there's no h's there, so k just stays k as h approaches 0. All right, so let's go put that in our chart over here. All right, so here on the chart, the derivative with respect to x of kx, where k is a constant, that's just k. All right, the next one here is derivative with respect to x of x to the n power, where n is any constant. So that power could be lots of different things. We could have a positive number, a negative number, a fraction, all kinds of different things. So you'll notice that these next few examples are just lots of different examples of powers. And so let's go through this first one in a little bit of detail, and then I'll just quickly go through all the others. So derivative with respect to x is limit as h approaches 0 of f of x plus h. I'm going to go ahead and put x plus h into the function. So x plus h, the quantity squared, minus f of x, that's just x squared all over h. And then I'll go ahead and expand out the x plus h, the quantity squared. And then I have the minus x squared at the end. You should have done enough of these that at this point you know what's going to happen here. So I have some terms that cancel. I have an h that I should be able to factor out. And that allows me to cancel with the h that's in the denominator. And then I have an expression left. And I can go ahead and take the limit as h approaches 0. Okay, so there's a lot of letters here, but h is the one approaching 0. So we're going to use a substitution shortcut theorem and substitute in 0 for h, not for x, for h. H is the thing approaching 0. So I get 2x plus 0, or just 2x. Okay, so that's one example of what was in that next rule in the chart. The next rule in the chart was for x to the n. So this is what we get when I have x to the n, where n is 2. And then there's a whole bunch more examples here. And so the idea is that we want to notice what are the patterns in these results. So I'm going to go through all of these next ones quickly. So we really want to focus on what the result is. You might pause the video and try some of these on your own, and then just double check with the video once you restart it and make sure you're getting the same thing that I get. Okay, so I've just done a bunch of powers, x to different powers here, and what we want to look for is patterns. And the patterns are easiest to see in these first few that we did here. I want to focus for a second here on examples 4, 5, and 6. So I want you to focus for a second here on the original function and then the derivative. Original function and derivative, original function and derivative. And so you might notice for all of those that it appears that what's happening here is that if you have an original function of x to some power, the derivative has that coefficient out front, that is whatever the original power was, and then the power here is 1 less. All right, so we just need to make sure that that pattern still works when I have not just positive whole number exponents, but fraction exponents and negative exponents. So on this next example, our original function is square root of x. So x to the 1/2, if I'm going to write that as a power. And then what I want to think about is whether the derivative would be, if I have the whatever the exponent was, that becomes the coefficient, so 1/2, and then the power is 1 less. Noticing the same pattern like we had in that previous one, when I had x to the 5th, notice that the power on the derivative was 1 less. So 1 less than 1/2. So if I just think about 1/2 minus 1, that would be negative 1/2. And I want to check to see that's what I got. Is that the same as 1 over 2 square root of x? And it is. All right, so it seems that our conjecture that this pattern of coefficient out front came from the previous exponent and power is 1 less holds, at least for that one. Let's check these others. All right, so I'm going to rewrite the original function in terms of exponents. So 1 over square root of x is the same thing as x to the negative 1/2. And then I want to think about whether the derivative is what I would get if I have that original exponent. So in this case, negative 1/2 as the coefficient out front. And then the exponent being 1 less. So if I think about negative 1/2 minus 1 is what I'm thinking about here for the derivative. So the exponent would be negative 3/2. And I want to see, is that the same as what I got when I used that definition? And it is. It's just written in a slightly different form. I have negative 1 over 2 times x to the 3/2 on the denominator, but that's the same thing as what I have here. All right, so what I've done here is not really a proof. A proof would be doing this in general, but I've looked at a whole bunch of different examples here to notice patterns that we get. So I'm just going to quickly go through and rewrite each of these in terms of what the original function is, and then using that pattern, what we'd expect the derivative to be. All right, on this one, just thinking a little bit carefully about fractions here. So I know a lot of students will grab a calculator when they see something like this, but you are going to do this so often you really want to get to the place where you can do this in your head. So you just want to think about 1/3 minus 1. That's really 1/3 minus 3/3. 1/3 minus 3/3, and then that's easy to subtract those fractions in your head, so you get negative 2/3. And that does verify with what I got here. All right, and then this last one here, if I rewrite the original function in terms of a power, I have x to the negative 1/3, and then I try out what I'm seeing here for the pattern, where the derivative would have the original exponent out front for the coefficient, and then the exponent is 1 less. So see if you can do this one without having to grab a calculator. Negative 1/3 minus 1. So that would be negative 1/3 minus 3/3. So negative 4/3. And that does verify with what we got when we use that limit definition of the derivative. All right, so at this point, I think we can feel pretty confident that we can say that that rule works. Again, what I just did here is not really a proof. You actually need some stuff to do an actual proof of this that you maybe haven't seen before. So we're not actually going to prove it. It's proved in the appendix of our textbook if you want to look at that. But just going ahead and writing down that rule that we saw based on the patterns here. So the derivative of x to a power, on that derivative, the power, what was the original power, will be out front for our coefficient. And then the new power will be 1 less. So n times x to the n minus 1. All right, and then I have one more to do here. One thing to notice about this, sometimes students try to apply the same rule, but it's not the same kind of function. Notice that one of them has the variable in the base of the exponent, and the other one has the variable in the exponent. So it's a different kind of function, a different kind of rule. So let's go ahead and look at this one. We'll take our time going through this one. Okay, so that is example 13 here. So we're going to just start by using that limit definition of the derivative. And then there's a little trick in this one, a little bit of algebra that maybe you hadn't thought about before, but if you kind of go back to basic exponent rules and think about that, if I have a power and another power of the same base and you want to combine those, you add the exponents. And so usually you use that property this way where you add the exponents. Here I'm actually going to use that property the other way, and where I have the e to the x plus h, I'm going to rewrite that as e to the x times e to the h. And why that's helpful is that I can then factor out an e to the x. Okay, and again, there's a lot of letters here, but e to the x is times this, and so really I can separate this into a product here. So I have e to the x times, and then all the h's are over here. All the other problems had the x's and h's kind of more intertwined with each other, but in this one they end up kind of separating into separate factors. All right, so the issue here is I need to figure out what this limit is, and notice that I can't use a substitution shortcut there. Notice too that there's not really the same kind of algebra that I could use on those other problems where I can do some sort of expanding or rationalizing or something like that. So this limit here is a little bit more difficult. It's actually a special limit, sort of like our sine x over x as x approaches 0 limit that can be proven using some specific techniques, but we're actually just going to use some numerical values to estimate what we think this limit is. So I'm going to bring in here a table that I already created. Okay, so here you see actually two tables, one of them where I have h values that are bigger than 0 and approaching 0 from the right, and then the output values of that e to the h minus 1 over h. And then my second table where I have h values that are less than 0 and approaching 0 from the left, and my output values of the function there. And so we can see that from the table, we can estimate this limit to be 1. It appears that these values here are both approaching 1. So if that really is true, it actually is. What I did right there with the table is not a proof of it, but we would get e to the x times 1, which is e to the x. All right, so this is a really unique function. Notice that all the other functions we looked at really, the function and its derivative are different functions, and I've kind of made a big deal about making sure that you don't write equals between a function and its derivative. But on this one, notice that the original function and its derivative actually end up the same. So this is really a special kind of function that has this unique property that it is its own derivative. So let's go up there and put that in that chart. All right, so this function is its own derivative, just e to the x. All right, so I just put these all here in this chart in the notes. You also have a yellow derivatives essentials packet that has these as the first 4 items on one of the pages that has basic function derivatives, so you might put those on there. And that's a good thing to use to study and look back and use as a reference really for the rest of the semester, and if you're going to take Calc 2, really for Calc 2 as well. All right, in the next video we will look at some examples.